Now that you've gotten to see how mammals breathe, it's time to take a look at bird breathing. Birds have a pretty sophisticated ventilation arrangement. So in addition to having lungs, they also have a network of air sacs. So I've pulled an illustration from your textbook that's over here on the right-hand side. The lungs themselves are this structure up in the top, and then you can see this collection of air sacs surrounding the lungs. And in birds, the lungs themselves don't actually change in volume, they stay the same size, and instead air gets moved through the lungs using a bellows type of action. And there's still a lot of outstanding questions about how that type of movement is accomplished. But let's take a look at an overview of kind of how air passes through that. So we'll take a look at this YouTube video.
The avian respiratory system is the most efficient in the animal kingdom. The primary functions of the respiratory system are to supply oxygen to the body tissue and to carry away carbon dioxide produced by high levels of metabolic activity. In birds, this process of gas exchange is crucial because the demand for oxygen during flight is enormous. The flight muscles must receive a large and constant supply of oxygen to maintain flight, and metabolic wastes must be removed quickly. Unlike most land vertebrates, birds lack a muscular diaphragm to power respiration, and instead rely upon expansion of the rib cage to draw in air. When a bird inhales, air actually leaves the lungs. Fresh, oxygenated air enters the lungs as the bird exhales. The avian respiratory system is composed of the trachea, relatively small lungs, and usually 9 large air sacs. These 9 air sacs are extremely thin-walled and do not play a direct role in gas exchange. Instead, they serve as bellows to bring air into the bird and store it until expiration. They allow a continuous stream of air to pass through the lungs in a one-way flow, thus producing the most efficient respiratory system of any vertebrate. They are also connected to certain pneumatic bones, aiding the bird in shedding excess heat from its body as it breathes, which would be fatal if not removed. These air sacs include a pair of cervical sacs, a single interclavicular sac, a pair of anterior thoracic sacs, a pair of posterior thoracic sacs, and a pair of large abdominal sacs. All of the air sacs participate to some extent in the respiratory process. All of the posterior air sacs expand on inspiration, while all of the anterior air sacs contract on expiration. The path of a breath through the system can be summarized in 4 steps. During the first inhalation, the breath travels down the trachea, into the left or right bronchus, through the lung, and into the posterior thoracic and abdominal air sacs. As the bird exhales, the abdomen contracts, forcing the air out of the abdominal sacs and into the lungs. Within the lungs, the air passes through parabronchi and eventually through air capillaries. It is only here where the exchange of carbon dioxide for oxygen occurs. As the bird inhales again, the air within the lungs is driven out. The now stale air passes into the interclavicular, cervical, and anterior thoracic air sacs. During the second exhalation, the anterior sacs contract. The air is then driven out into the trachea, where it passes up and out of the nostrils. This specialization of the avian respiratory system is one of the greatest factors in flight. Without this unique anatomy, the act of flight would likely be impossible.
Okay, so as you saw, there's a very sophisticated arrangement of air sacs. Since we are a physiology course, we're not an anatomy course, I'm not going to be asking you a lot of detailed questions about the names of each of these different air sacs. So in general, what I want you to focus on is the fact that the anterior air sacs, so the air sacs that are closer to the head, play a different role than the posterior air sacs do, okay? So don't worry too much about knowing anything about the abdominal sac compared to the cervical sac, for example. Just mainly focus on anterior and posterior for our purposes. So as that video showed you, I want to just reiterate that with the breathing cycles for birds, air actually leaves the lungs when birds are inhaling, right? So as a bird inhales, the posterior air sacs are going to expand, and the anterior air sacs are going to expand, right? So that's going to draw air through the lung and out of the lung, okay, during inhalation. So air exits the lung during inhalation, and then as the bird exhales, air will be pushed out of the anterior sacs and it'll leave the body, and it will also be pushed from the posterior air sacs through the lungs, okay? So during inhalation, air basically bypasses the lungs, heads to the posterior air sacs. Then during exhalation, that air is pushed through the lungs. Then during the second round of inhalation, that air moves into the anterior air sacs. And then from that point, when the bird exhales again, that air will leave the air sacs and leave the body. Okay, so kind of two different ways to sort of visualize that four-step process. But again, a big takeaway from this is that air is going to flow through the lungs in a single direction, right? This is contrast with what we've seen in mammalian breathing systems, which are tidal, right, where air goes in and comes out. Instead, every time air travels through the lungs, it's always fresh air. There's no mixture with stale air. Okay. So let's take a closer look at the structures in the lungs of a bird. And bird lungs are composed of a set of parabronchi, and the parabronchi are then in turn constructed out of a set of what are called air capillaries. This is a fine network of small tubes, similar to blood capillaries. And if we look at this in very close cross-section, the air capillaries mingle very closely with blood capillaries. There's a lot of blood supply flowing through the bird lung, unsurprisingly. And here is where we finally encounter our last form of gas exchange. So birds use cross-current gas exchange. And that, might raise a question, how do we know that they're using cross-current gas exchange? Well, we know thanks to a really innovative experiment. Basically, scientists have tried flowing air backwards through a bird lung, and what they figured out is it doesn't matter which direction you flow the air through the lung, forwards or backwards, you get very similar gas exchange efficiencies either way. Now, if you think about this for a minute, if birds had been using something like countercurrent exchange and you flowed air backwards through the lung, you would see a dramatic drop in gas exchange efficiency, right? Spend a little bit of time thinking through that just to make sure you get that idea. But again, that was very compelling evidence that birds are not using countercurrent exchange. Instead, they are using cross-current exchange. This has always left me with a little bit of a question. How on earth did birds wind up with that type of lung arrangement? Where did that come from? So to answer that question, we're going to go back for a second and look at a couple of interesting examples of breathing systems in some non-bird reptiles, specifically alligators and monitor lizards. So there's a relatively recent set of papers that have come out in monitor lizards and in alligators that show that the anatomy of both of those reptile lung types promote a very similar airflow dynamic to what I just showed you for birds. So monitor lizards, as pictured here, and alligators also engage in unidirectional airflow. So they have a similar set of lobed sacs, and that facilitates movement of air into the posterior sacs and then back out through more anterior sacs. So I think by seeing how this works in alligators and monitor lizards, we can start to imagine how we wound up with the breathing arrangement that we now find in the birds. And that actually takes us through bird breathing. So in our next video, I will take you on a tour through invertebrate breathing systems.